Hello and welcome to a new session for this online course on Introduction to Embedded System Design. I am your instructor Dhananjay Gadre. In this lecture we are going to look at one of the most important aspect which forms an important part of the ecosystem for a microcontroller to function effectively, namely clock and reset sources. We have seen in a previous lecture that a microcontroller require 4 very important elements: clock, reset, power supply and an ability to download code into the memory of the microcontroller. In this lecture we are going to deal with the first two issues, namely clock and reset. Now, why does a microcontroller require a clock? The reason is a microcontroller is an example of a synchronous digital circuit, and because I have used the word synchronous, that means it is going to use a clock signal, and therefore, I must provide such a signal. Also, the value, that is the frequency of this clock signal, will determine lot of things. The frequency, higher the performance, because your microcontroller will be able to execute more instructions per second if the frequency is high, but it will come with a price, and the price is that as the frequency gets higher and higher, the power dissipation will proportionately increase, because the power dissipation of a CMOS circuit is directly proportional to the frequency of operation. And so, we must decide what is an optimum frequency for the operation of the microcontroller at any given point of time. Fortunately, and it was one of the salient features which I had mentioned in the salient features of microcontrollers, MSP430 offers the ability to be able to dynamically change the clock frequency using a software, using the user program. The user can decide at any given point of time, do they want a higher frequency for operation because the performance requires so, or if there is no work to be done, there is no point in clocking the microcontroller at a high frequency, and instead a lower frequency of operation could be selected so as to conserve available power. So, let us look at the clocking options of MSP430. This is the block diagram of the clock module which is there inside MSP430. On the left you have the sources of clock, and on the right of this diagram you see signals which are derived from these 3 sources. There are 3 sources, this is one of them, an internal VLO clock that is called, an external crystal based oscillator and an internal digitally controlled oscillator. These are the sources, and using a particular combination of these 3 sources, the MSP430 clock module offers 3 signals, clock signals. It is called a clock, that is auxiliary clock, the main system clock and a subsystem clock. Let us see what these clock signals do, what part of the microcontroller do they serve, and how their frequency can be changed. This is a simplified block diagram of the clock module as applicable in MSP430 G series. You have a very low frequency internal oscillator, it operates at about 60 kilohertz, we will come to the details. You have a low frequency crystal oscillator. The oscillator is inside the microcontroller, the crystal has to be connected to external signals, external pins, and apart from that you also have a digitally controlled oscillator. There are 3 multiplexers, multiplexer number 1, number 2 and number 3, and each multiplexer has 2 inputs broadly, and you can write software to select one or the other source of clock. Once you decide the clock source, it can be further divided with a clock divider using an option of divide by 1, 2, 4 or 8 to derive 3 clock signals, and these 3 clock signals are auxiliary clock, master clock and subsystem master clock. Let us see what these clock signals are used for. So, as I mentioned, there are 3 sources: digitally controlled oscillator, low frequency crystal oscillator and very low frequency oscillator inside the MSP430. The digitally controlled oscillator is based on a RC, internal RC oscillator, and let me give you a very simple circuit that may illustrate how a RC circuit can be made using a logic gate such as an inverter here. This will oscillate at a certain frequency as determined by the value of this R and this C. This is not to suggest that the DCO uses this is just an example. Anyway, the digital controlled oscillator allows you to change the frequency of operation in this range from 60 kilohertz to 16 megahertz for a certain supply voltage. If the supply voltage is changed, these numbers, these upper and lower limits would change. It is a RC, controlled RC oscillator, as I have mentioned, and because it is a very quick start oscillator, it can start working in less than a microsecond. It can be used to get out of low power modes of operation. We are going to consider low power modes of operation of MSP430 in a subsequent lecture, but this digital controlled oscillator allows you to switch from low power modes into active modes of operation. The DCO frequency, digitally controlled oscillator frequency, can be adjusted by software by writing appropriate values in various registers. In the program you can change the frequency. The default frequency after reset is 1.1 megahertz. So, if you do not do anything and you just reset your microcontroller, you do not have to make any selections. The value of the DCO frequency will be 1.1 megahertz, and this is the source of the clock. As you see, this part in the block diagram here, lower side, is highlighting the DCO clock, and all these names that you see here, these refer to various bits in various registers that we will see very soon, which allow you to change the frequency of the DCO oscillator, digitally controlled oscillator. Further, you have a multiplexer here, as we had seen in the simplified block diagram, which allows you to select the SM clock here, as well as you see here, this signal goes and feeds to the master clock also. We come to that shortly, but so this is the part about the source of clock source, that is the DCO. Then apart from the DCO, we also have the low frequency crystal oscillator. You can use a low or a high frequency crystal, but for the G255 series you are restricted to a low frequency oscillator, and that is recommended at 32 kilohertz, and in fact the exact frequency is 32768 hertz. This is a crystal used in real time clocks, and so is very commonly available, and this is low frequency, which is used with for the low frequency crystal oscillator, which is inside the oscillator is inside the microcontroller. This crystal has to be connected to external pins X, as we have seen. If you had a different microcontroller apart from other than this, you could use a higher frequency crystal also. Here is the part highlighting the low frequency crystal oscillator. These are the X in and X out pins onto which between which you connect a crystal. This is the crystal, and in the case of our current microcontroller MSP430 G2553, this crystal can be only 32768 hertz. It can be other frequencies also, but it just so happens that you will have to get such a crystal custom made. This is the most common commercially available crystal. The third source of clock is very low frequency oscillator. It is also internal RC based oscillator, and the typical frequency operation is just a mere 12 kilohertz, and you can imagine that from 16 megahertz for the DCO down to 12 kilohertz here, you can really change the frequency operation and therefore change the way the microcontroller performs functions and the amount of power that it consumes. Here is the source, clock source, and as you see it feeds a multiplexer here. Now, the question is, we have seen here that we need a auxiliary clock, we need a main system clock and we need a subsystem clock. What is the purpose of having multiple clock signals on a microcontroller MSP430? And the reason is low frequency operation is best for energy conservation. It is also good for timekeeping. The high clock frequency will allow you to react to external events in a short time, and therefore, that is beneficial when you want to respond quickly. And if you want a stable clock, then having a crystal based oscillator is the best option. And MSP430 allows you all the three options. It offers you very low frequency RC based oscillator, it allows you a 32.768 kilohertz crystal based oscillator, and it allows you another RC based oscillator whose frequency can be digitally altered to go from 60 kilohertz on one end to 16 megahertz on the other side, and so you could select that if you would like to have fast response time. And that is the reason why multiple clock sources have been provided and the clock signals can be derived from these clock sources. What are the clock signals that we need? As we mentioned, one of them is master clock. It is used by CPU. CPU has only one clock signal and that is master clock. Master clock signal can also be fed to other peripherals. As I mentioned, after reset, the default master clock is derived from the DCO with a frequency of 1.1 megahertz, but you can select the master clock signal to come from low frequency crystal oscillator, to come from VLO or the DCO, and XT2, that is a high frequency crystal 2, but this option is not available on our microcontroller, this particular microcontroller part. This is the part where you are selecting the master system clock here, and as you see you have a divider which allows you to further divide the frequency. You have a multiplexer which allows you to select which source, clock source can be used. Master clock can come from here, and this itself allows you to select either the VLO or the low frequency crystal, and the other part of this multiplexer is being fed by the DCO. So, master clock can be derived out of VLO or low frequency crystal or DCO. Then the other signal that we need is the subsystem master clock. It is distributed only to peripherals. This is not fed to the CPU. Oftentimes it is the same as master clock, and the if at reset the value is from the DCO and the frequency is 1.1 megahertz, and again it can be selected from low frequency, it can be sourced from the low frequency crystal oscillator or the VLO oscillator or of course the DCO clock. Here is the part about subsystem master clock, and the third is the auxiliary clock. This is again only distributed to peripherals, and the source of auxiliary clock can only be the low frequency crystal or the internal low frequency oscillator. If now both these oscillators are slow oscillators, meaning when you apply power to them, they do not start oscillating quickly, they take some time to build up and for the oscillations to stabilize. And because of this, if any peripheral is being fed from the auxiliary clock, you must make sure that the oscillators have stabilized. If the oscillator has not stabilized, the microcontroller will not connect the clock source to the clock signal and therefore to the peripheral. And this we will see later how we can detect whether the oscillator is stable or not, and if it is not stable we can wait. And why we can wait? Because the CPU which decides which clock is to be fed to which peripheral, the CPU is being fed by master clock, and we can choose the master clock to be from the DCO. So, it can continue to perform, the microcontroller can continue to run the program, but in that program you can wait for these oscillators to stabilize before you apply to any peripherals. Here is the selection for the auxiliary clock. Again it has a divider, as you see, you can divide the source, which is either this or this, by 1, 2, 4 or 8. Now, in the DCO, apart from the ability to vary the frequencies, it also has 4 calibrated frequencies, and those are 1 megahertz, 8, 12 and 16, and you can write values into appropriate registers to select whatever frequency you want. This is a sample code that 2 registers, one of them is called BCS control, the other is called DCO control. By writing appropriate values, these are basically bit masks. By writing this into these 2 registers will result in a DCO frequency of 1 megahertz calibrated frequency, not 1.1 megahertz, but quite accurate 1 megahertz frequency. Now, sometimes and oftentimes when you want to measure time accurately, you may not want to use the DCO, you may want to use the low frequency crystal, because a crystal is a very stable and accurate source of frequency, in which case you have the option of selecting the low frequency crystal oscillator. Traditionally oscillators, crystal oscillators offer you large range from 32 kilohertz up to few tens of megahertz. In our MSP430G255 series, we are restricted to 32 kilohertz crystal, and it is designed to give you the printed frequency at 25 degree centigrades. In the case of MSP430, it has to be connected between these 2 pins, that is X in and X out. Where do you use crystals? When you want to measure time or when you want to measure frequencies of events, then you should consider using a crystal. A crystal oscillator also requires capacitors. Some capacitance is already on the microcontroller, but you, depending upon the recommendations of the data sheet of the crystal that you use, if it requires more capacitance, then it can be connected to the X, these 2 pins, X in and X out pins, extra capacitance on these pins as the requirement may be for a particular crystal that you choose. Okay. Now that we have seen the sources of clock and the clock signals that we need, here are the registers which allow us to select various sources, decide their frequencies and route these clock sources to appropriate auxiliary clock or master clock or subsystem master clock. The most important register is the DCO control register, and it has 2 sets of bits. One is called the DCO bit, and these are 3 bits here, and you have 5 bits here which are the mod bits. The DCO bit selects a frequency, broad frequencies, which are dictated by another set of bits, which are these bits, which we will see in the other register that we will briefly see. These R cell bits allow you to go from 16 kilohertz to 16 megahertz, 60 kilohertz to 16 megahertz, and within that these bits will tell you what particular frequency you can operate at. If you want to have a frequency selection even finer than you can get with DCOX, then you have to play with the mod X bits. For introductory applications, for simple applications, you do not have to worry about this. Now, this is the second important register, basic clock control register. Here I want to make a point. Do you notice that some of these bits here, it says, when it says RW means these bits can be written to as well as read from, and then it says RW, here it says RW dash 0 and here it says RW dash 0 within a bracket. These two refer to different values of 0 depending upon the source of reset, and we will consider this when we consider the reset case, reset facilities in MSP430, but I just wanted to bring that to your notice. In this register, basic clock control register, we do not have this option because as I mentioned it does not offer you high frequency crystal. You can select this, only this option is available, and using this you can decide whether you want to which divider you want to use for the auxiliary clock. And these are the R cell bits, these 4 bits which decide broad frequency ranges that run the DCO oscillator. Then you have the basic clock control register 2. Here this decides whether what is the source of the master clock, meaning these bits, these 2 bits will decide, will select the multiplexer which is feeding the master clock source. These 2 bits will decide what sort of divider do you want to use for the master clock source. This will decide whether do you want, how do you select the sub master clock, and you only have this option here because this is not available on our MSP430 G2553, and then these 2 bits will allow you to choose the divider for SM clock, and then this bit allows you whether you want to have an external resistor. This is not available on our G2553 series. This is the third register, basic control register, clock control register 3, and here you have several bits, but the most important bit is these which allow you to choose what sort of frequency crystal you want to use and whether you want to use internal capacitance, what will be the value of these capacitance. Now, to set the frequency of the DCO, you have to write into the DCO register as well as the second register, that is basic clock control register 1, and I suggest that you go through this slide to understand all the options. Based on the bits that you write into these registers, you see this is part of the data sheet that allows you to change the frequency from 60 kilohertz to 16 megahertz. Now, we want to illustrate the great flexibility that MSP430 offers by dynamically changing the clock frequency. And what are we illustrating here? Let me show our plan. What we are doing is, we are going to take a MSP430. As you know that there are 3 sources, VLO, crystal low frequency crystal oscillator and DCO. We are going to select the very low frequency oscillator for the master clock, which means the processor will operate at 12 kilohertz, but the 12 kilohertz basic frequency can be divided by 1 or 2 or 4 or 12, which means by selecting an appropriate divider we can reduce the frequency of operation for the CPU, because I am saying we will select the master clock from master clock signal will come from VLO. What we want to show is as follows. We want to have a LED like this, and in fact we are going to use the existing LED on the lunch box, but we want to connect 3 external switches with pull up resistors. One more, here VCC, and where are these connected? Where are these 3 switches connected? They are connected to P 1.3, 1.4 and 1.5. So, let me write here P 1.3 pin, P 1.4 and P 1.5, and as we know the LED is connected to P1.7. What do we hope to achieve? That we will start the oscillator, we will select the VLO to go through the multiplexer and provide the signal for the master clock. And then we will have a program which will continuously poll these 3 switches, and if this switch is pressed, for example, it will divide the VLO frequency by 1. If the second switch is pressed, it will divide it by 4, and if the third switch is pressed, it will divide it by 8. Thereby, you will get these 3 resultant frequencies. You see, if you divide by 1, the source is 12 kilohertz, therefore, the frequency will be 12 kilohertz. The CPU frequency, that is master clock frequency, will be 12 kilohertz. If you divide it by, if you choose the divide by 4 option, you will get 3 kilohertz, and if you choose the 8, you will get 1.5 kilohertz. And you can, how would you know that the oscillator, that the CPU is working at different frequencies? Well, what we will do is we are going to blink this LED. We are blinking this LED at a certain rate, which is derived out of the clock frequency. Basically, what we are saying is turn the LED on for some clock cycles and turn the LED off for some clock cycles. Now, if the frequency of operation reduces, you will see that the duration of the on and off increases, that is frequency goes down. And so, by operating it at let us see, P1.3 is here, you get a 1.5 kilohertz clock, here you get 3 kilohertz clock, and here you get 12 kilohertz clock. Of course, we have further used delays, so that the LED will be blinking in visible range. You can you can observe that the LED is turning on and off. It is not that it is turning on and off at such a high rate that it is beyond the persistence of vision. No, we have written the code in a manner that it is you can see that it is turning on and off, but the rate of blinking will be perceptibly different when you choose these clock frequencies. So, let us go through the code to understand how it works. At the beginning, we see, as usual, we have included the header file. Then we have defined that we are going to put the LED on bit 7, but bit 7 is not telling the actual port pin. Bit 7 is simply a mask bit, as we have seen. Then we are putting one switch at bit 3, bit 4 and bit 5, and these are all P1.x. So, here it is P1.7, 1.3, 1.4, 1.5, all right. Then we have a function which we call as switch input. I will come to that later. We have another function called register settings for GPIO. I will come to that also, and we have third function which is called register settings for the VLO. And then we have the main program. So, the main program is really very simple. What is it doing? When you reset the system, the first instruction that is executed is to stop the watchdog timer. We do not want to be bothered by watchdog timer overflowing and resetting us, which we will see in the next part of this lecture. Then we are calling this subroutine, which is basically selecting the VLO, and based on the switches, it is going to select a particular frequency operation. And then we are calling another subroutine where we are deciding the direction of the pins of the microcontroller. The P1.7 pin has to be output pin and the other 3 pins have to be input pin. That will be done in this second function. And then we have a infinite loop while 1, and we are saying read the switch. So, I am going to go execute this function in which I am reading waiting whether switch 1 is pressed or 2 is pressed or 3 is pressed. If a particular switch is pressed, it will go and change the frequency operation of the VLO oscillator, and will come back here, and then it is going to. So, this part of the code is simply toggling the LED. So, you toggle it once, go back, wait for the switch to be pressed. If it is not pressed, you come back, again toggle the LED. So, you keep on doing it, which means most of the time you are toggling, but after every toggle you are going and checking whether any switch has been pressed. If any switch has been pressed, you wait for it to be released, and then based on which switch was pressed, you are changing the VLO frequency. And so, after that when it comes here, you will see that the LED toggle rate changes. Why? Because the CPU clock itself has changed, and this is therefore a great example to illustrate how MSP430 offers you dynamic clock stability. Let us go through the code again. Switch input, here we are waiting whether switch 1 is pressed. If it is pressed, this is to debounce, and then you are selecting that the VLO divider should be by 8, therefore, you will get a frequency of 1.5 kilohertz. If switch 2 is pressed, then you debounce it again and select this divider, so that your resultant clock frequency, CPU frequency is 3 kilohertz. And the third option is, if the third switch is pressed, your VLO will not be divided, it will be the same as the VLO frequency, therefore, the CPU clock will be 12 kilohertz. Then this is very simple, it simply turns the pin which is driving the LED as output, and the other 3 pins P 1.3, 4 and 5 as inputs, it does not do anything else. And then this second function, which allows you to select various select VLO as the source. As we saw earlier, you have to play in the basic clock source register 3 to select the VLO oscillator. Now, as I mentioned, this is a slow oscillator, and therefore, after power on it may not quickly turn on, and if you go through the data sheet of MSP430, it will tell you to wait for certain amount of time before you can expect this clock to work. And the way to check is to reset a particular flag in this register, which we will see in the reset part, and you turn this bit to 0 and wait for some time, and if this bit remains 0, that means the oscillator is stable. If the oscillator is not working properly, the microcontroller will set OFIFG bit again, and so you are going to wait in this loop till this bit is reset to 0. If this bit remains reset to 0, that means the oscillator is stable. Now, you can make this setting will allow you to route the VLO oscillator as the master clock. So, you are doing those two things. One, you are selecting VLO to come out of the first multiplexer, and then you are using the clock signal multiplexer to select master clock from VLO. And so, here is the implementation. We have connected, as you see, these are the 3 switches 1, 2 and 3. These are the pull up resistors, and this LED, the user LED on P 1.7 will blink. So, I suggest that you have downloaded this code, rebuild it and upload it into the lunchbox, and see how the blinking rate of this LED, changes as you press this or the other one. The rate is quite perceptibly different, and this is the proof that by pressing the program can decide what can be the frequency of operation for the CPU, also what can be the frequency of operation of other peripherals. So, this is as far as the clock frequency operation, the clock sources and clock signals of MSP430 microcontroller are concerned. We have covered that. Now, we are going to look at the reset part. Now, why does a microcontroller require reset? It is because a microcontroller is a logic circuit. A logic circuit uses flip flops, and the flip flops may have arbitrary values when power is first applied to them, and this may lead to non-uniform operation, and therefore, it is very important that all the internal registers are initialized to a known value when the system is powered on for the first time, and that is the function of reset. There are broadly two types of resets, one is called power on reset and the other is called power up reset. There is a fine difference between the two. Power on reset happens, as the name suggests, when the power is applied for the first time, but power up clear can happen from other sources also. Now, power on reset is generated whenever you turn power for the first time. It can also be generated because there is a brownout. Brownout means that the supply voltage to the microcontroller is not stable. If it dips below a certain value, it will reset the it will generate a power on reset for the microcontroller, as well as if you press the reset NMI pin, that will also generate a power on reset signal. Now, what reset the system? Is it possible to find out what was the source of reset? Was it brownout? Was it power on reset, that is turning the power off and on, or was it the user pressing the switch on the RST NMI pin? Is it possible to find out? Yes, MSP430 microcontroller has registers which capture the source of that reset, and in fact, in this segment we are going to write a code which will show which sources of reset was the reason the system was reset. Power up clear, on the other hand, is generated because of software conditions. So, the primary difference between power on reset and power up clear is that power on reset is because of external conditions. Why? You are powering the device up, so it generates a power on reset, or the supply voltage is not stable, so it generates a reset, or a user presses a switch on the RST NMI pin. These are all external events, but power up clear is generated because internally something has happened, and one of the reasons could be the watchdog timer. Of course, whenever a power on reset signal happens, that also generates a power up signal, but additional to that, a watchdog timer or a security flash memory access violation or a CPU trying to fetch something from the peripheral address range. Each of these 4 events could lead to a power up clear signal being generated. What happens in them? Whether it is power on or power up, the system is going to restart fetching the first instruction as pointed to by the reset vector. The after power on reset, the RST NMI pin is in the reset mode, that is, it works as RST pin, not NMI pin. The IO pins are all switched to input mode, and other peripheral modules and registers are initialized to a known value, which you should refer to the data sheet and the user guide for exact information. Now, this is what I had mentioned earlier. Each of the registers, when it is reset or when it is cleared, meaning when it is POR or PUC, will be indicated under that register. If it is written like this, that means 1 RW means it can be read and written, and 0 means that the after PUC the value will be 0. But if it is this, that means only on power on reset the value will be 0, only on power on reset, which means if the power up clear condition has been generated because of some internal event, the state of that bit may be 1 if prior to that event this bit was 1, that is the difference. So, this is because of POR and this is because of PUC, this nomenclature, that is RW-0 indicates a PUC condition and RW dash bracket 0 means this is only achieved on a power on reset condition, not power up clear condition. After system reset, which means whether it is because of power on reset or power up clear, the status register is set to 0. That means, if you have been operating on in low power mode, you will come out of it. The watchdog timer becomes active in the watchdog mode, and the program counter is loaded with the reset vector location, which is this, and as we have mentioned, 2 locations are required for the address of the memory where our program is located, and these 2 addresses are FFFE and FFFF. After the system reset, you must, if you wish, you must initialize the watchdog timer, and usually you turn it off, and you must configure the peripheral modules. That is the responsibility of the program. This indicates brownout reset if the voltage falls below a certain level here, and here the system is reset. Only when the voltage exceeds this can the system start working. Please go through this slide to understand how brownout reset works. Watchdog timer is a very important peripheral. It is actually part of a general purpose timer, which can function either as a timer or it can function as a watchdog timer, and we can choose which mode of operation do we want that timer to operate at. The primary function would be to as a watchdog timer, because there are other timers which are available which you could use for measuring time. This particular timer is often dedicated for use as a watchdog timer. Now, what does a watchdog timer do? That if you allow the watchdog timer to function, depending upon the source of clock to the watchdog timer, it will count up, and if you do not reset it, eventually it will overflow, and the overflow signal will generate a power up clear signal, which means you are going to reinitialize the system, you are going to start executing the program using the vector at the reset vector. Now, if you enable the watchdog timer, how do you ensure that the watchdog timer does not create a power up condition? Is to frequently reset the watchdog timer, because when you reset the watchdog timer, it will start from 0 again, it will count up, and before it expires, meaning before it overflows, it is your responsibility to reset it. In case you forget to do that, it will create a power up condition, and we will see later in a code here, we will see how watchdog timer can create a power up clear condition. The watchdog timer can count up to these many bits, that is, it is a 15 bit, although the timer itself is 16 bits, for watchdog purposes it has a 15 bit limit. You can also choose lesser values, which means the watchdog timer can be made to count lesser number of clock signals, and then it can generate a power up clear signal. In the interval mode, it can work as a conventional timer, and we will see this when we are talking about the timer operations. Now, to control the watchdog timer, there are 3 registers to worry about. One is the watchdog timer control register, the other is a interrupt enable register, this is a special function register, and the other is a interrupt flag register. In the watchdog timer control register, it is a 16 bit number, 16 bit register, and it is password protected. It is a read write register, which means if you want to write, you must also supply the password, and we will see what is the password. This is the password, and if you read it, you will, in one part of the register, you will get this value. These are the bits, as you see, this is a 16 bit register, this is for password, read or write, and these are the effective 8 bits. Let us go through them, the important ones. This is used to hold the timer, meaning with this bit you can stop the timer. with this bit you can decide whether you want the RST NMI pin to act as RST pin or NMI pin. As you see here, if you write a 1, it will function as NMI pin, and if you see go back here, you see this indicates that at power up it will retain the previous value, but on power on reset it will be 0. This bit allows you to select the watchdog timer as watchdog or a timer, and this bit allows you to reset the watchdog timer from, so that it can restart from 0, and this bit allows you to select a source of clock for the watchdog timer. You can select either the SM clock or the auxiliary clock, and this allows you to decide what is the number of counts that it will count before it overflows and generates the power up clear signal, and you can go from 64, a count of 64 to 32768. This will give you the maximum amount of time before the watchdog timer kicks in. So, this interrupt enable register, we will see which bits are useful for our operation. If you set this to 1, that means you want to use this for as a timer function. If the this bit is inactive in the watchdog mode. The other is if the oscillator fault, if there is a fault in the oscillator, this bit will be set to 1. This is when the NMI interrupt happens, and the last one is whenever you try to access regions of flash memory which are not accessible to you, this interrupt will be enabled, meaning if you enable this, an interrupt will be generated when you try to access flash memory which you should not, and so on. So, as the important point to note here is that this bit is not is only applicable for the watchdog timer in a timer mode, not in the watchdog mode. And then we have the SFR interrupt flag register. Now, this is very important because this is telling me lots of flags related to various sources of resets, and we are going to use this in our code. If this bit is 1, that means the source of reset was a watchdog timer. So, as we see, set on watchdog timer overflow, meaning if you have enabled the watchdog timer and this the watchdog timer overflows for whatever setting of the clock and whatever bits to count, if this bit becomes 1, that means the source, it would reset the it will generate a power up clear, and this bit will be 1. On the other hand, if the let me look at the reset parts. If the power on reset was generated, this bit will be 1. If the external reset, meaning the pin was pressed, this bit will be set, and if the NMI pin was used, then this will be set to 1. And what is this? This is the oscillator fault, meaning whenever the VLO or the low frequency crystal oscillator is unable to start, this bit will be set to 1, and the user has to keep writing 0, and if the oscillator is not starting to function, the microcontroller will set to 1. So, you write a 0 and wait for some time and then check, is it still 0? If it is still 0, that means your oscillator is working. And so, this is the part I was referring to earlier. Let us see what we do now. To stop the watchdog timer, you simply write these two values into the watchdog timer control register. These are basically this part of the instruction, this part of the register is supplying the password, and this is telling that please reset the please stop the watchdog timer, and we will you see how its use in our program example. So, now what we have done is we have set up a experiment which this is the code for it, and we want you to download this code. Now, instead of testing the code on the lunchbox, we want you to just download the code into the lunchbox and then remove the IC and insert it on a breadboard and connect few switches, well no switches, few LEDs to indicate what was the source of reset. We also want you to connect one switch, but that switch will be connected to the RST pin. And with this setup, we will be able to identify was the source of reset the watchdog timer overflow, or was it power being applied for the first time, or was it because the reset pin was pressed. This program allows you to do that. Now, for that we have used 5 LEDs. Whenever whatever be the source of reset, the program will start executing. As we have mentioned, the master clock which supplies to the CPU is derived from the DCO at 1.1 megahertz, and so immediately upon whatever be the reason for reset, the microcontroller will start working and this LED will be turned on. This LED is connected to P1.0. Then when the program actually runs in a loop, this LED which is P1.1 will toggle, will blink. On besides this, the program will try to identify what was the source of reset. If the source of reset was power on reset, that is you had turned the power off and you turned it on again, LED on bit P1.2 will turn on. If on the other hand the watchdog timer overflow happened, it will turn the LED on P1.3, and the third option is if you press the reset switch, the LED on P1.4 will turn on. And so, I recommend that you go through the code. Let us go through this. Here we have first stopped the watchdog. This is the main code. We are going to go back to the part of the code which has some functions. This is first we have turned the watchdog timer off. Then we have selected the auxiliary clock to operate at this. Using the crystal, divide by 8, so that we are operating at 4 kilohertz. What is it going to do? It is going to feed to the watchdog timer. Why do we want such a low frequency operation for the watchdog timer? So that you can get some time after, let us say, power on reset or the user reset. If the watchdog timer is fed with a slow frequency clock, it will give you time before the watchdog overflows, and you can see that initially the source of reset was, say, power on reset or the user reset, and then when the watchdog timer kicks in, you will see that the system resets again, but now the LED corresponding to the watchdog timer will turn on, and that is why we wanted to give time, and so we have chosen a very low frequency crystal oscillator. Here is a code which allows you to set the bits appropriately. You want those port 1 bits to be outputs, and now you are waiting for that oscillator to stabilize, and then you check the reset source. Now, also in this we will go and see the code in this. The moment you, the first program that runs is you of course turn the watchdog timer off, then you enable the auxiliary clock, and then you run off to execute this register settings for GPIO part of the code. Let us see what it does. Here it simply makes these bits as output PDIR, and then it simply turns LED 1 on, and it turns all the other LEDs off. So, LED 1 is on. The moment you see LED 1 on, meaning your system is working. Now, what will happen is you go back to the main part of the code. Now, you are waiting for the oscillator to stabilize, and this may take some time. After that, you go and check the source of reset. Let us see that code here. So, in the reset, how do you check the source of reset? You have to look at this register here. This register, by identifying various bits, you will know whether the source was watchdog reset, or whether it was power on reset, or whether it was user reset button. This code basically looks for that, turns appropriate LED on and goes back to the main program, and in the main program once you have checked the source of reset, it simply goes in an infinite loop of toggling LED 2. So, here is the how the circuit has been connected. Although I am using a lunch box and it appears to have a microcontroller here, I am not using this microcontroller. I am using the lunch box only to derive the power supply from here. This is the MSP430 which you could have taken away out from your MSP430 lunch box, inserted here. As you see here, here is the crystal. So, you need to connect a 32 kilohertz crystal for that oscillator that I mentioned, and the rest of the connections. And then here is this is LED 1, this is LED 2 which is going to blink. This will turn on the moment power is applied, and these are the 3 LEDs which indicate the source of reset, whether it is power on reset, whether it is user reset. This is the user reset pin, the switch, and the third source could be the watchdog timer. So, I recommend that once you have programmed your microcontroller in the lunch box with this code, take it out gently, insert it into the breadboard using the crystal oscillator and other stuff, connect these LEDs and see how the microcontroller is able to find out the source of reset. So, this is what we have for you in this lecture on sources of clock as well as various ways in which MSP430 microcontroller can be reset. I will see you very soon with a new lecture. Thank you.